So basically what we can do is, if you have to define an image as a function, the rectangular grid which I showed you in the last slide, that acts as a like a range of domain of that function. Let's say that function is p, and the values that function p can take is any of the grid cells. Okay, so it will be like x comma y coordinate, and then it will store, like, each grid cell will store a value which will be like the range of that function, and it is called like the pixel value. Okay, that's how you represent your images in form of functions. And this is just exactly showing that. So this is your grid, and each of these like white circles over here, these are like your coming from your domain, which are like the representing the grid cell in this xy coordinate, and the grayscale value is actually the range, what value we are storing at that particular location. And again, that can have like some discrete set of values. So you know that we're talking about like the bit depth of an image, right? So that bit depth actually defines the range of your image function. So then this xy grid is kind of domain of that function which you are using to define your image, and the values which these locations can store, they represent the range. Same goes for RGB images. It's just like, instead of single channel, it will have 3 channels, and each channel will have a domain and a range. The domain is not going to change because all these 3 channels corresponds to like the same space. And again, the range will also be same most of the time. If it's 8-bit, it's going to be 0 to 256. Now let's try to understand like how sampling and this digitization actually affects the actual images. Now, the first step of digitization was sampling. So sampling will define what will be the resolution of your image. Okay, so if you're going to sample like at very bigger steps, which means that your image will have a very small resolution, let's say on the left. But if you are going to sample like very closely, then your image resolution will be very high and the quality will be very good, which is shown on the right. So sampling has a direct correlation with the image resolution. Okay, and if you think about this, your cameras has this metric, right? Megapixels, how many megapixels your camera can capture images at. So that represents the sampling rate. The second step, which is quantization, it actually indicates the quality of the image which you're going to see. If you're going to like create discrete steps at a distance, then it means that you are actually using a very low bit depth. For example, just 4 colors, you're going to see something like this. And if you are going to use like your discrete steps which are very close to each other, then you will get like a very high quality image. Okay, so these two are like both part of digitization, but they like correlate to different properties of your images. Now, there's another interesting aspect. Again, it's resolution, but it's different from the resolution which I told you, like the image resolution, which defines like how many pixels you have. It's called dots per inch. This has significance to like 3D, your 3D environment. Okay, and the idea here is you might have heard that your images has like, let's say 72 dpi or 300 dpi. This is kind of a norm, which means that if you measure the distance of like, let's say inch in a real world, then how many pixels that 1 inch will be. So this is also called resolution, but it's different from the resolution we were talking earlier. Right? So this will define like when you try to print that image, let's say in a paper, then what will be the quality. Okay, because this has like the real correlation with the actual distance in your 3D environment. Okay, so this DPI is dot per inch. It's saying over here, and this is entirely different from the sampling part which we were discussing. All right, so again, this is a simple example like covering all of those things, and this is showing you actually like how your pixels are actually discrete. They are not continuous, right? Because this is kind of a coarse scale we are using. And again, at each pixel, you can see that what value is being stored. And that value is again not continuous. So it's showing both the aspects at the same time. All right, then just one last point here. This is really important. So images are not just like images which you capture using your regular camera, right? Images can have different forms. And when we do computer vision, we might have these RGB, these normal natural images, but these are also like images. So this is, let's say, ultrasound, this is your MRI, and this is infrared, right? All these kind of different modalities of data can also be represented as images. So there is something to know, because when you are developing your algorithms, it's not going to be just operating on this kind of image. You might have algorithms or similar kind of algorithms which might also operate on these kind of images. Okay.